Naming compounds. So to begin here, we should see a cyclopentene, and the ene takes precedence in our numbering. And so we have cyclopentene, or if you want, you could call it 1-cyclopentene, or if you want, you could stick the 1 in between the T and the ene. And then taking care of the groups, 3-bromo and 5-methyl. For the second one, we should see 6 carbons, and numbering from right to left places the ene between 2 and 3, so we should call that hex 2-ene or 2-hexene, whichever way you prefer. And then cis-trans isomerization is possible in alkenes, and if the like groups go in opposite directions off the ene carbons, that is what we call the trans stereoisomer. May as well take care of the one right below it. Same numbering system, only this time from right to left. And now the similar groups go in the same direction off the ene carbons. And so we're going to call that cis hex 2-ene or cis 2-hexene. Here we have a cyclohexene, and numbering it gives this sec-butyl group located on the 4th carbon. And again, you can say 1-ene or 1-cyclohexene, but you don't have to if the ene begins at 1 and 2. The molecule right below it is very similar in that it's a cyclohexene. Again, 1-cyclohexene. And now this 4-carbon unit in position number 3 is 3-isobutyl cyclohexene. In this molecule, we have a 5-carbon chain, and there's an ene between 2 and 3, so we would call that pent 2-ene, taking care of the groups 2-chloro, 3-bromo, pent 2-ene. And lastly, prioritizing groups on the ene allows us to designate this as E or Z. We can't use cis or trans because these two groups are not the same, nor are these two groups exactly the same. So we have to prioritize each group on the ene carbon. Higher priority bromo over ethyl. And here we have higher priority chloro over methyl. And now the highest priority groups go in opposite directions, so that is the E stereoisomer. This one is vinyl chloride, common name, systematically 1-chloroethene. Here we have just basic cyclohexene. This one, common name, allyl bromide, and systematically 3-bromopropene. And this one is just butene. No possibility of cis or trans. The rest on that page, which two are stereoisomers? That would be the cis and trans molecules with the same formula otherwise. And which two are structural isomers? That would be those two. Which one do we use to make PVC, also known as polyvinyl chloride? Of course, it's vinyl chloride. And which molecules would form stable carbocations? NEL-lilic halide. And to make a carbocation means bromide leaves, carbon left behind, that the bromide left from is positive, and that is stabilized through these two interconverting or two resonant structures. They don't really interconvert. There are different versions of what the overall thing is, and that's the allyl cation. Number 2 is just simply informational. In making alkenes, we take a halide, treat it with a base. The base is always abstract hydrogen, causing an elimination overall, and it follows Zaitsev's rule, which means the most substituted alkene is favored. In the next one, we're dealing with 2-methyl 2-bromo-butane. Simply draw a butane, 2-methyl 2-bromo. Quickly realize it's a tertiary halide. Read the problem again. We're treating that with NaOH and water. And the NaOH is a base, which can also, of course, be a nucleophile, hydroxide. Water promotes ionization, so our solvents don't really give away the whole answer. The next sentence says we're trying to make alkenes, so now we know it's elimination and substitution. SN1 and SN2 are ruled out, so now your hydroxide's going to act as a base. And then lastly, if we look back at our halide, we should recall that tertiary halides with loss of bromide, a good stable leaving group, can somewhat readily form carbocations, and the fate of the carbocation is determined by the base, and those two carbons are equivalent, would result in the same alkene. This carbon is different than those two, so we can get two possible alkenes when our base picks off that hydrogen, making that alkene as these fold in between the CC, one of the C's being the carbocation. And that's a tri-substituted alkene, which Zaitsev says is favored over the di-substituted alkene, and this would result from the base abstracting that H, these electrons forming an alkene. So that would be your Zaitsev product. Number 4, most alkenes react overall by addition. Number 5, mercuric acetate, sodium borohydride, oxymercuration, demercuration, that results overall in B, Markovnikov addition of water producing an alcohol. Hydroboration oxidation, the reagent system is diborane or BH3 followed by H2O2, and this would give you the anti-Markovnikov product. Number 7, hydrohalogenation, and hydrohalogenation in peroxide just exemplifies Markovnikov addition product and the anti-Markovnikov addition product. And I did not draw the H's in either of those, but this H would go on this carbon based on Markovnikov's rule. When you use peroxides, the H actually goes on the opposite carbon and the bromide on that carbon. So this indicates two regiochemical outcomes of hydrogen halide addition. And for the mechanism, I would certainly choose the easier of the two, which is without the peroxides. I redraw my alkene and my HBr. Quickly realize that the nucleophile alkene pi bond is going to grab a proton, displacing the bromide, and that is going to result in the more stable secondary carbocation over the primary, plus a bromide anion, and the bromide anion can then attack from either face the formed carbocation to result in that halide. And it would be a racemic mixture, as this carbocation is achiral. Next up would be these reagents, or this system causes diol formation from your alkene. So you simply draw the carbon skeleton without the double bond and add 2 OHs. The next one is cleavage. So draw the carbon skeleton, do not draw the ene double bond. As the cleavage is going to put O's on both carbons of what was the alkene, forming aldehydes or ketones, and in this case it's a dialdehyde. Bromination of an alkene occurs with specificity, and the specificity is that it occurs anti. So this molecule, the 2 bromines are added from overall the same face, that's syn, so that product would not be formed. So B definitely would be formed, but recall that you also get the enantiomer of B. There's no way to get meso, as this does not have a plane of symmetry. And number 10, epoxides are just cyclic ethers formed when an alkene is treated with metachloroperbenzoic acid. And recall, a per acid is when there's an extra O in addition to a regular carboxylic acid, and it's this O that would get inserted into an alkene through a paracyclic-like reaction, making this triangular cyclic ether, which we call an epoxide. This is questioning regio and stereochemistry. If it occurs with overall syn addition, that means it's stereospecific. So now you can rule out D, A, and then between B and C, you're talking about regiochemistry. If you get a mix of anti and Markovnikov products, then it's not regio-selective or specific. So non-regio-selective, but stereospecific, B. The next one just asks if you know oxymercuration, demercuration causes overall Markovnikov addition of water. So this C of the ene has more H's, so it preferentially gets the H, and this C must therefore get the OH, forming that alcohol. In hydroboration oxidation, it's the opposite, so you get the anti-Markovnikov, where the carbon with fewer hydrogens gets the H, and the other carbon gets the OH. In halohydrin formation, that's the reagent system. What happens is overall you add Br and OH across the ene double bond. And mechanistically, here's the arrow movement for how that would lead to that brominium ion. Bromide minus would also be produced, and then this ion is opened up by water, and water we can show many ways, but I'll show it like that, and it's going to attach to the more electropositive carbon of the intermediate, even though it's not formally positive. That's again tertiary like, opening up, gives you that, which would then lose a proton, forming the product alcohol. Just for fun problems, recall from number 7 that we were doing hydrogen halide addition, in this case HBr addition to that alkene, which we should all say results in this carbon gaining the H, forming that carbocation, and we should recall carbocations are prone to rearrangement. This would certainly rearrange to that because this one is benzylic. If you were asked for a mechanism, it would be a hydride shift where this leaves with its electrons and attaches next door, moving the positive to where the H was, and then the benzylic carbocation is captured by the bromide ion that was formed in the initial carbocation formation to result in that halide. For this one, we have classic acid catalyzed hydration, which would result overall in Markovnikov addition to this ene. So this C gets the H, this C gets the OH, resulting in a secondary alcohol, which when oxidized produces a ketone. In this case, same ene, we get the opposite hydration product. So now we would get the primary alcohol, which when oxidized will initiate